Butterword.
Hello, children. I heard the cat was out of the bag.
Mr. Butterworth, that's terrible. It already says that on the paper.
But that's what I was reading. I was reading what we were talking about.
Oh, okay. Now it makes sense.
All right. So we got to look at some designs. Oh, we did that last time, so we should be good at this game. So we've got 1, and then we got 3 and 3. No, it was 2 and 2 and 3 and 3. So I bet the next one, I'm going to do it. This next one's going to be 4. Whoa, what was that?
I don't know.
That's not what I wanted. There we go. 4 and 4. I changed my pen so it looks prettier.
Cool.
Did I do it right, Mr. Carlson?
That looks great to me. I noticed that as each design goes up in design number, it looks like we're adding a block to the top and to the side. So is that where the 4 and 4 came from and stuff?
Yeah, and I just looked at it and I said design 1 had 1 block. Design 2 has 1 block. I mean 2 blocks like that and 2 blocks like this. Design 3 has 3 and 3. So I said design 4 had to have 4 and 4.
Cool. And then I noticed that you put 1, 3, 5. Is that the total number of blocks?
Yes.
And that would make this one have 7. And then to me, that looks like we're going up by the same amount each time.
That is true. So that's like an addition thing.
Cool. I like it. Okay. So we've got a whole bunch of patterns that we've used previously. And here it's talking about growth patterns. That's how many items we have going from one design to the next design. Miriam. Okay.
I'm just writing down Miriam's name and writing down her pattern. And then I'm writing down the ballot because I figure we can talk about it when I write it down.
That makes sense.
So we've got 1, 9, 16. And really the overall heading of all of these is kind of 1, 2, 3, because the first thing was 1, the second thing was 9, the third thing was 16, that sort of thing.
Cool. The third thing is not 16, it's 25.
Oh, goodness. I don't know how to count. I'm sorry. I had that in my brain because some of my students noticed that there were 16 around the outside. That's why it was.
Oh, that makes sense. Cool. So in looking at that, I think we had that discussion in the last video where we talked about that's going up by a different amount each time, but the pattern itself was not too bad to find, or at least in terms of looking at like the bottoms are going up by the same amount each time. It's going up by, so the first bottom row was 1 and then 3 and then 5. And then the last one, M&M. Oh, from Maureen and Matthew. I get it now. So in terms of that, we have some kind of a growth pattern that's not quite irregular, or not quite regular, but seems to be going up by a predictable amount. The second one, I go from 3 to 6, and then 6 to 12, and then 12 to 24. That's the one that we talked about it doubling each time.
Yeah, I think that's the easiest pattern to see.
I think so too, because
if you look at Miriam's and you know something about, well, if you look at the shapes, we talked about that squaring kind of idea.
Yeah.
But the ballot one's just doubling each time. I think the M&M one is a little bit tricky, the Maureen and Matthew, because I agree, there's definitely a fixed pattern that we talked about last time. But just looking at the numbers, it's not quite as obvious.
Yeah, I agree. Because I can see that we're going up by 5 and then we're going up by 7. I think the next one does go up by 9, if I'm correct in remembering that, or I could just be making stuff up, but that may be.
It would have 26, so yes, 9.
Yep. And one of the things we talked about that was it's growing the inside but not the outside.
Yeah, so I remember we talked about not thinking this as 5, but thinking of it as 3 plus 2. And then, 8 plus 2? And then 15 plus 2?
Sorry, I'm knocking stuff over on my desk here.
And trying to figure out a pattern for that.
Yep.
All right, so we
Cool.
figured some stuff out.
All right, I think that's a pretty good start for kind of thinking about these things. All right, so now we're going to use patterns to build expressions, and I like that we're using the same patterns that we just spent a little bit of time digesting again. So that's the total number? Cool. And describe the pattern of new tiles that are added to each design. Ooh, that's a different question.
Ooh, I should read it carefully. New
Uh,
tiles that are added to each design. So we
so,
added 8. My students talked about this, and then we added 16.
cool. And here we added 1 because the previous design had 0.
Yes.
How many do you think we'd add for the next one?
Well, let's see. We've got row 5, so we'd have a row of 7. So it'd be 14 and 10, so 24.
Cool.
That took me a little bit to process. If I took 2 off of each end from
Yeah, no,
7, how
I
many
saw
I had?
that. And then how about we don't talk about changing from a design that doesn't exist to that one? That seems kind of silly.
Okay, so we got 8, 16, 24. So that looks linear.
That makes, yes, that makes sense to me. I was thinking about the total number, and that doesn't make sense.
No,
But
I was like, does he not know how to add 8 each time? What's he stuck on here?
that makes sense to me. Okay. And that's linear because we're going up by the same amount each time. And by that, we're going up by the same amount by adding each time really is the key there.
That's why I wrote plus 8.
I like it.
All right, so for here, we have to write an expression, not an equation, an expression to represent the number of new tiles only, that must be added to an n by n square floor design to build the next design. Let n represent the number of tiles along each edge of the square. So for example, n would be 3 and n would be 5.
So when I saw this, one of the things that I noticed is that every design that we have, so the next one would be 7 by 7, which we've talked about before. We're adding 4 tiles around the outside. And then I noticed something really cool about the other tiles that we're adding. However many tiles that it was, were the same number as tiles that we had in the previous design. Or I'm sorry, however many tiles on each side that we're adding was the same number as the previous design. So for the 3 one, we were adding 4 tiles around the outside. Actually, I'm going to make that red so it matches.
Oh, I like that. I crossed out the design numbers because I think that is a confusing thing to add to this.
Yeah,
So if we
and
just focus on the blue numbers down the bottom, I think that will help.
I think so too. And not that we would ever do anything like this, but we totally didn't spend 5 or 10 minutes recording this, hate the way that we did it, and go back to the beginning for this slide.
We
Never
are
did that.
perfect and would never make that mistake. That would be, we totally did that. I'm sorry.
So what I notice is that I'm adding 1 tile, but 4 of them. So I'm going to call this 4 plus 4 times 1. And then here we had 3 tiles going to 5 tiles. I've got my 4 red tiles. And then I've got 4 sets of 3 tiles, which was the old number that I used to have. So it's 4 times 3. I predict that for the design of 7 that we purposefully did not draw, and we talked and thought about that beforehand, that we'd have the same 4 red, and then 4 times this whole length of 5. The question here is really asking about n tiles, so a number that we don't know. And how do we get to the next one? So this would be like n equals 1, n equals 3, n equals 5, n equals 7.
So what I'm seeing is as you wrote those numbers down the bottom, when you wrote n equals 3, which I just circled, if I compare that to the number in the parentheses, there's a relationship there. And then n equals 5, if I compare that to the number in parentheses, there's a relationship there.
By the way, you were circling the wrong parentheses each time.
I did? I circled that one.
But when you said n equals 5, you circled that parentheses.
Oh, I circled this number down the bottom first. It doesn't matter. Anyway, stop wasting time, Mr. Carlson. We're not allowed. So is that n minus 2?
But we don't want to go, that's why you were circling the wrong number, because you want to know for the next one, not the previous one.
Oh, I see what you're saying.
So to figure out 5, we use this formula to get the next one.
Ah.
So to me, then that would look like 4 for the corners plus 4 because we have 4 sets of them. And then however long that side length would be, which we said was n.
I like it. Sounds good. So let me reiterate. So we had the 4 fixed corners. There's always a piece in the corner. And then what we're really trying to do is we're trying to get from, say, the n equals 3 one. We want to figure out how many tiles do we need to add to get to the n equals 5 one. And when we added that, that's what this expression up here is.
That's correct.
And so that's why we have we see the 3 right in there and the 3 right there. So that's why the n is there.
Cool. I like it. Mr. Butterworth, I noticed that says class on the other question here. Do you think that's one that would be good for students to ask about in class if they need some support?
Yeah, they should try it and see what they can figure out because they might be able to figure that one out. But if they can't, I agree. They should ask us.
Excellent.
All right, now we have Ramon determined an expression to represent this pattern. His expression and explanation are shown. Explain why Ramon's expression is incorrect. So Ramon built a table. In the first part, he has design. In the second part, new tiles. So with design 1, we have 0. With design 2, we have 8. With design 3, we have 16. He wrote the expression 8 quantity n minus 1 represents Miriam's square floor pattern. I notice the number of new tiles is increasing by 8 in each new design. I like what he's saying. I like that we're saying we increase by 8, but I think the flaw is connecting the design with the letter n, and that is not what they're asking us to do here.
Now, is that because each of these are talking about an n by n square?
Yeah.
So that was some of the discussion we had in the last one, like changing that, our thinking, and you cross some stuff out because that was confusing.
Right, because those are the extra numbers on the design made me want to use those numbers, but I shouldn't be using those numbers because they had nothing to do with the n.
And that's exactly what Ramon did as well.
Correct. We forgive you, Ramon.
All right. Hey, we're back to Miriam again.
Well, she's the boss in this situation.
Oh,
we
it's
got
true.
Miriam in charge.
So we've got going from design 2 to design 3, and each one uses a unique method. I'm guessing that we're going to have a couple of these different methods to take a look at over the next few slides. So for Wilma's, we have this description, and she's saying it's 4 times 3 plus 4.
That's what you did.
That is what I did. That looks a lot like what we did. So we want an algebraic expression to talk about. So we said this was like 4 times n, where n is the number of the one that we're adding to, and then plus 4 for the corners. The way that we had written this before was a little bit backwards. It was 4 plus 4 sets of n tiles. Now, is it okay that we wrote this both ways?
Of course it is, because we're doing addition. And in addition, we can move things around. It's called the commutative property, Mr. Carlson.
Cool, I like it. That's a good property to remember.
Now we have Howard. And Howard said, I must add 5 tiles to 2 of the sides and 3 tiles to the other 2 sides. The number of additional tiles is, holy moly, 2 times 3 plus 2 plus 2 times 3. So I think what Howard is saying is, if I use what you said on the previous page, keep the 2, keep the 2, and keep the 2. Because I think those, Howard is saying, are fixed.
So just to kind of process that, the 2 here comes from the 2 tiles that he's adding to the ends.
But I thought there were 4 tiles.
But he has 2 sets of those.
Is that where the other 2 comes from?
So the 2 in that is going to make the 4 total.
And what about the random plus 2 at the end? Oh, that's a 2 times 3, right?
Yes, I was like, I don't know where that is.
Yeah.
And then there
Oh,
are,
so that has to do with that red side that you just talked about, the little bracy side.
yeah, so we've got 2 sets of those as well.
So is it fair to say replace any 3s with the letter N?
I think so, because that's really talking about there's the 3 plus the 2 we talked about. There's the 3. That makes sense to me.
Beautiful. And these are ones we're asking them to try to process, and then we'll talk about in class. So
I
that's
like
what you
it.
should do, is you should try to process those, and we'll talk about those in class.
Oh,
This
look,
is
this is
also
another class one.
the class one.
So we just had 4 different ways of looking at this. And one of the nice things that I liked about this is that all 4 of these ways were mathematically correct. And thinking about which one makes the most sense to use is a good question.
Is there only one answer to this question, Mr. Carlson, or could we create arguments for any of the answers?
I don't know if we could create arguments for any of them, but I would say that we can probably create arguments for at least all of them.
That was very confusing, but I'm going to accept it.
I like it. Ooh, Michael and Louise. So this is Tamara's method. I don't remember what Tamara's method was.
Well, this one says student answer, so I think that they should have to answer that one.
C10.
I think that's the question 10. We'll get there.
Oh, okay.
So we'll just keep going. They're good on this. And see,
Oh, look.
we didn't tell them that we already did all the work for them here.
I
And
like it.
hopefully they don't figure that out and they've already done the work, because that would be good.
That would be excellent. So calculate the numbers of tiles with a side length of 135 to create the next design. So we
Does
want
that
to
mean
use
we
all
plug
4 of these.
135?
It does.
Oh, okay.
Do you want to do the ones on the top? I'll do the ones on the bottom.
Sounds good. That was confusing. I thought you were going to say left, then you said
I
top.
was, and then I noticed that the left ones are easier than both right ones. So I figured that I would do something like that.
So I'm just plugging in 135 for n. And then I got to get my calculator out because I'm too tired to do all this work. 135 minus 1 is 134, and then plus 4.
And then I'm just adding 135 4 times.
That's a lot like multiplying by 4, huh?
I know, it really is. So I feel like that's going to be like, I don't know, 540. I don't know where I got that number from.
I think you used your calculator. Let's see.
It.
Now I got to do 2 times 137 this time, and then add 2 times 135.
We're going to have some issues.
I forgot to add the 4 on the previous one.
Okay.
That's what I just learned because I got 544, and I'm pretty sure these are supposed to be the same answer. 544, and I got 544. Told you I'm having a day.
Oof. So then we've got 137 squared minus 135. Thanks, buddy.
137 times 137 minus 135. Wow, that's a big number, times 135. I got 544, Mr. Carlson.
Oof. So all 4 methods, we got the same number.
Whoa, good job, Wilma, Howard, Tyler, and Tamara. Tamara or Tamara?
I think it probably depends, because I've had students named Tamara. I know that there are people named Tamara.
Oh, so it's like my daughter, Naomi versus Naomi?
Yeah.
Mm.
At least this name makes sense to be pronounced both ways. I'm not going to really go into that argument, though. Cool.
All right, so now we have Wilma tells Miriam that since all of the expressions result in the same solution, any could be used. Miriam thinks that the employees need to use more values in the expressions than just one to make this conclusion. Who is correct? Wait, this is their job. I read it for them now. I'm the
That's
best.
very nice of you. All right, so we're talking about equivalent algebraic expressions here. That means that these things look different, but actually would be the same. That's actually a really big deal in mathematics, that we have things that look different but actually end up being the same. You're going to do that in every math course that you take from now on, which is kind of fun. So we're trying to show that these have to be equivalent. Do you want to do 2 and 2 again, Mr. Butterworth?
No, you can do the pink one, and I'll do all the rest.
That's what I was thinking too.
Because the pink one looks scary.
Okay, I got you.
So for Wilma, I'm going to use the distributive property. Are you going to use the distributive property?
I am. I'm going to use the distributive property. I like that I wrote the problem wrong immediately.
Because I started talking to you. I'm sorry.
And then I'm going to, even as I'm writing this, simplify n times n, write that as n squared.
What I just noticed, Mr. Carlson, is remember how on the previous slide I definitely had a mathematical error?
Yes, it's because you make lots of mistakes.
But I just assumed that I had added wrong.
Oh, you mean you didn't?
No. What I realized was the expression that we wrote down for Wilma, that we wrote down prior to today, when we're doing this recording, is different from the expression we wrote down 3 minutes ago for Wilma.
Oh.
So Wilma's supposed to be 4n plus 4.
Oh, okay. So that
So
one, you don't even need to combine anything. That one's already kind of simplified for you.
right. So 4n plus 4 is where we're starting on that one. Whew.
Hey, and now that matches Tyler's, so that's pretty good.
It does. And with Tyler's, all I did, it was combine like terms, which sounds fancy.
All right,
Carlson, you're falling behind, friend.
I know. I'm going back to my difficult problem. So you got n times n gives me n squared because I've got to use double distribution. N times 2
I only
is
have to use
2n.
single distribution.
2 times n is 2n, and 2 times 2 is 4. And the other thing that I notice here is that we've got n squared minus n squared. So I think those are going to cancel each other out.
That does seem correct.
2n plus 2n is 4n, and then plus 4. Hey, we got to the same place.
Now, interestingly, in your work for Tamara, you have the 2n plus 2n plus 4. And in my work for Howard, I have 2n plus 4 plus 2n. That's again an example of the commutative property. And we can move those around, and they're really the same thing.
It is. I like it. Ooh, a new activity. This one's about patterns of growth.
No, this is the same, though. Because we did this question already. Remember, it was the homecoming question. So it's a new activity, but it's really an old activity.
Okay.
And we already drew this picture, except we used dots, I think.
We did, because stick figures are way too hard for us to draw. We're not artists.
I see. This was the doubling one. So we went 3, 6, 12. I was using the laser, so mine went away.
It's true. You were. I figured you were doing that as you said that, and then as I wrote that, which is fun. All right, so we've seen this. We talked about this is doubling each time, and we're starting with 3. We're going to be completing some tables here. We're going to have you pause and try to complete this on your own, and then come back to see how you did. And with the magic in our brains, we put things on your papers or on your screens.
We're the best. Look at us with match. See, I was gonna go bam when we came back. just to freak him out. But the numbers showed up. So what we did is we wrote down the 3, 6, 12, 24, 48, 96. Mr. Carlson kindly added the times 2 next to those numbers to show what the pattern is. Now, really, if we wanted to, now that you see the numbers, I'm going to erase them all. I swear I clicked on the eraser and didn't want to go first. All right. So instead of 6, I'm going to write that as 3 times 2. And instead of 12, I'm going to write that as 3 times 2 times 2.
Cool.
And instead of 24, okay, I'm going to just keep writing. So if you notice, there's a pattern.
You're running out of space. Is there a way that we could shorten like 2 times 2 or 2 times 2 times 2 to make that less full of stuff?
Yeah, I'm teaching Algebra 1, and we're just talking about exponents. Let's use an exponent.
Oh, cool.
So you're saying I can do 3 times 2 to the 4th?
Yes.
And 3 times 2 to the 5th?
Yes.
Wait, 4 and 5, 5 and 6. There's a connection.
Oh. And
I
like
noticed
this
that
is
3 is
2,
always there.
that's 2 to the 1, and that's also 1 less than 2.
Oh. And this would be technically on the next to the 3. There's 2 to the 0 there, right? Because 2 to the 0 is 1.
It would. So would it make sense if we said this was for n? I'm going to go a little below so I can write this clearly. 3 times 2, and then if this is our n for that row, this is going to be n, and then whatever. How do I write like n but 1 less than n?
N minus 1, friend.
Oh, cool. I like it. And this would be our expression. All right.
Sweet.
We also added a graph for this, just based on the data from the table. And then I kind of connected the dots to make a smooth-ish curve in my excellent art skills. The question that goes with this is really about, do all of these points make sense? And to me, the red dots make sense because those are the days that we're looking at. But like, we don't talk about like 4.2 days in terms of the people that find out things, although I guess you could.
We could. See, my initial thought was no, it doesn't make sense. But as you talked, it actually talked me into it.
Yeah, I talked myself into it too.
Yeah, the only sticky part would be, obviously some of those points will have like partial humans, and that's not a thing.
Yeah.
And so for those, it doesn't really make sense. So I think in the context of this question, only the points that we have make sense because that's the data that we know. And it's not necessarily that it happens kind of at that rate each day.
I think that makes sense to me. All right, so we're describing this pattern as linear or exponential or quadratic. We said that the pattern was 3 times 2 to the n minus 1 power. And then the table, we had times 2 times 2 times 2, and our graph looked something like this.
And on the right, I wrote down what the various curves look like. This is with positive leading coefficients, which if you don't know what that means, that's okay. It's just what they generally look like. So linear functions is just a line. An exponential function has like a swoopy thing. And then a quadratic is like a U. But it did say, Mr. Carlson, write an equation. And that is not an equation what you wrote down.
Yeah, I agree. So this is an expression. Maybe making this into an equation that we can graph would be like a y and an x thing. So I could call this 3 times 2 to the x minus 1.
You could also, you could have written it up here. You could have said, I don't know, P of n.
Sure.
Where n is the number of days and p, that looks like pu. Sorry, I was on the edge and like started doing something weird.
I got you.
And where n is the number of days and p is the number of people. So, but it doesn't matter. I think the y and the x is probably an easier thing to approach.
Yeah, but I do like that we wrote it both ways. So I think that's helpful for us to talk about that. So it asks, how does each representation support our answer? Did we decide which one of these that is? I don't think we actually decided yet.
Which one of what?
Which is it, linear, exponential, or quadratic?
Oh, I mean, I did. I don't think we said it out loud, but given that I drew this graph, which looks exactly like what we have, I think I'm going to go with exponential.
And that's a really good, I think, description of how the graph supports that decision. To me, the table supports that because I know exponential means we're multiplying by the same amount each time. You might call this a common ratio.
It's also geometric in some lands. And then the exponential also makes sense for the equation because you have a letter in the exponent.
Cool. Key characteristics of our graph.
Swoopy.
It's swoopy. I also noticed that it goes up faster and faster and faster. And it seems to be coming down. What would happen if we kept going into the negative x?
It would get super close to 0. There's a fancy word that sometimes makes the children giggle called asymptote. And that would be back there at 0. So this curve will get closer and closer and closer to that asymptote, but never hit it. Again, if you don't know what an asymptote is, it's okay. We will get there.
Yeah, that graph is pretty bad asymptote.
It's true. I got scared when you started talking.
It's because I say scary things all the time. All right, and then we have a question that kind of follows up. How many days will it take 500 new seniors to learn about the election results?
I heard this, we're supposed to pause and let them do it. So hopefully they've paused by now. But we need 500 new seniors to know. So is that your P of N or your N, Mr. Carlson?
That's going to be our P of N. And I had to process this in my brain first because I was still thinking about how many new seniors total since the first day, not what this is asking. This is asking a much easier question.
Yes, this is not total because total, yes, total gets scary. So basically we have to ask this question. 500, stop being on that. 500 equals 3 times 2 to the who cares x minus 1. Now we don't know how to solve that equation algebraically. So what do I do?
While you do that,
like a table.
I'm going to consider this in a different way. Did we start with day 0 here? No, we didn't.
No, we started with 1. 1 was 3.
So you can keep talking while I build my table.
Okay, so Mr. Carlson's going to build a table. He's basically just using this information we wrote on the previous page and rolling with that. It seems like it's going to take a while, but it's not going to take that long. Another thing you could do is I wrote down that equation there, and there's this magical website called Desmos. And on Desmos, you could write y equals 500 and y equals 3 times 2 to the x minus 1 and see where they hit each other. And by see, I mean literally on Desmos, you can click and it will tell you where they hit each other.
Yeah, it's pretty great.
Mr. Carlson, you drew a smiley face.
I did, because I know that if I double 384, that's going to be more than 500.
Oh, so that's the smiley face.
So our answer for that would be on the 9th day. It's funny because it felt like that would take me a really long time at the beginning. And then suddenly the numbers got really big really fast.
That's the magical part of the exponents. And the next one, you guys should try yourself and then come to class if you are confused. Well, I remember this one. This was about the patio.
Oh, and this was, we talked about the number of tiles going across. I was trying to think of the word tile. I couldn't think of it. Was like the design number plus 2. And then the tiles going up and down, we said was the design number itself.
Yes.
And
but
then
we
we
have an
had,
area of that essentially, right?
Yeah, and then we had like plus 2 at the end for the entrance and exit.
Got it. But since we're talking area, as I said, we would take that n plus 2 and multiply by n essentially, because that's area, right?
That makes sense. That's not too bad. And then
And
we'd still have to,
we add 2.
we would. You beat me to it.
I did. But then you got to erase, which is my favorite thing to do. So since we're going to have n plus 2 and n, and those are being multiplied, that makes me think quadratic.
Mr. Butterworth, I have a question right here. I noticed that you put the n after the parentheses. Can we still distribute going this way?
We certainly can.
Okay, so that would be like n times 2 is 2n, n times n is n squared, and then plus 2?
Yes, and you use the commutative property just to confuse them.
I just went in the order that because I went that one first, then
Oh,
that
I see
one.
what you did. Yeah, I get it. I get it. But yes, that would be beautiful. I also could have put that n on the other side of the n plus 2, because again, in multiplication, we can use the commutative property.
I like it. And can I add any of these terms together, like 2n and n squared? They're both n's.
They are both n's, but they are not like terms because they do not have the same exponent. That is an excellent question, Mr. Carlson.
Cool. All right. And then we've got Maureen and Matthew. Maureen's expression looks different than ours does.
It does.
Um,
Oh, I see what Maureen did.
what'd
Wait,
she do?
I think this is like a Mr. Carlson move.
Totally is.
So she squared off the shape. So if I look at, this might blow up the world, but it will be okay. If I look at this design, tell me if this is what she's doing. Did she square off the shape like this?
Yes, she absolutely did.
Okay.
And it totally did just blow up the world.
And so she took the n plus 2 and n plus 2, and she had to multiply those for area, because this was the n, so n plus 2, and the n plus 2. So n plus 2 squared is the area of that whole square. And then she's subtracting out the parts I drew in.
And since n was like this much, that'd be the plus 1 from that.
Right, and that's again area, because it's n plus 1 times 1.
And taking away 2 of those is why we have minus 2 times that.
Yes.
I like it.
Sweet.
All right, then we've got Matthew's expression. Hey, that looks like the expression that we ended up simplifying to.
It is beautiful. Use technology to verify graphically the equivalence. Now, again, you can go to Desmos and type Matthew's expression in, and the one from the previous page in. You'll get these two pictures.
As a word of warning, you can't type in the words Matthew's expression into Desmos and have it do anything. You also may need to write this as x squared plus 2x plus 2 instead of n.
That is a good call, Mr. Carlson, because that's definitely what I did when I made those pictures.
And then we did this for you. These are the pictures that you should end up with. And like, to me, aside from one being a red solid line and the other being a blue dashed line, I can't tell the difference between those. Should I be able to?
No, they are the exact same thing. And the interesting part to me is part B. Identify the parts of the graph that represent this problem situation. So n represented the number.
The design number.
The design number, right? So actually, this graph I gave us is terrible.
You mean we can't have design number -1? That's not a useful...
We can't even have design number 0. They started it at 1.
Oh, so...
we only care about up there for the design.
That's interesting.
I feel like we just created a fountain there where you created a little dot.
Yep, and now it's...
That's pretty fun.
Shooting ectoplasm off into the space.
That's true. That made me think of those, what were they? Chillers or something? It had to do with Ghostbusters. And they were that really green color. They were like a juice drink when we were children back in the day. Ecto Cooler, I think.
Ecto Cooler. And they did re-release those for Ghostbusters Answer the Call.
Oh, so these humans might have seen Ecto Cooler.
Yeah. Those were awesome. Those are like the best juice boxes ever.
I don't know if that's true, but sounds
No,
good.
no, that is objectively true. That Ecto Cooler was the best juice box flavor ever.
I don't think such a thing exists of objectively true in that case, but okay. Now we got to do some algebra.
I'll do the stuff on the right if you want to do the stuff on the left.
I see no. All right, so the stuff on the left, be really careful. I would rewrite that. I'm going to write it above because we don't have that much room with n plus 2 and n plus 2. The reason I'm going to do that is because then, wait for it, we hear pew, 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 pew. We have to double distribute, as Mr. Carlson said. So n times n is n squared. N times 2 is 2n. 2 times n is 2n. And 2 times 2 is 7. Just kidding, it's 4.
Cool. I also notice we've got 2n plus 2n minus 2n. Could I just like cross out two of those 2n's since one's plus, one's minus?
Well, I'd cross out one of those 2n's, but yes.
Well, I need to cross out two of the 2n's.
Oh, that's true. I see what you're saying. I see what you're saying. Brilliant, Mr. Carlson. What about the 4 and the 2? 4 minus 2, I can do that. It's 2.
I like it.
So we have n squared. We still have 1 2n. And then we have a 2.
And hey, that looks a heck of a lot like Matthew's expression.
We did it. Don't tell them anything about this, but we just did a proof.
What? That sounds scary. I'm going to go to the next slide. Oh, look, it's the class problem.
So it's their job?
I bet this is one that they should use the stuff we did for the previous pages and try on their own. And if there are problems in it, we should talk about it in class.
That does sound glorious. I agree.
So until next time, I'm Mr. Carlson.
And I'm Mr. Butterworth. You have a lovely day.